Good morning and thank you for joining. We're going to let a few more people get on and then we will get started. All right, thank you for joining and we're going to get started. Today we've got the third and final presentation for Fike chemical suppression and isolation that is part of the explosion protection series that we've been running. If you have not seen the first two installments, please give somebody at Dale Prentice a call and we will send you the videos, or you can go to our website, prenticeco.com, and look for more information. Today we're going to focus on education. Once again, the primary, one of the primary corporate values, not only training our people, but also spreading the knowledge. We got Tony Svetko, on PE engineer, who's going to be presenting today, and then two representatives supporting the Great Lakes area for Fike products and explosion protection projects are Charlie Turcott and myself, Alex Primo. A few of the other things that VRC Protx and the Dale Prentice Company work on and can support your projects with are overpressure protection, isolation valves and actuation packages, control valves, as well as heat trace. We've got locations throughout the country, based here locally in Michigan at the Dale Prentice headquarters in Oak Park, and we've also got service centers at those following lists in Monroe, New Berlin, Hastings, Henderson, Colorado, Evanston, Wyoming, and Salt Lake City. Today we're going to be focusing on one of our core capabilities, which is explosion protection, and we'll get started with that right now. Tony, I'm going to pass it off to you, and thank you everybody for joining. Today we're going to have the introduction to explosion suppression and isolation of ducts and pipes.
Hello everyone, and welcome to this third presentation and introduction to explosion suppression and duct and pipe isolation. It's a big topic and we have about an hour, so that's why it's an introduction. And if you have any questions, please feel free to ask, or later on you can email or call Alex or myself or Charlie or anyone at our offices, and we'll be happy to discuss things with you. Common applications for explosion suppression. By far the most common application we run into is dust collectors, bag houses, bin vents, cyclones. Once in a while, bucket elevators are candidates for suppression when explosion venting is not possible. Storage hoppers and bins, silos, screw conveyors, spray dryers, and interconnecting pipes and ducts. We're not going to be going over the general standards. That was our first presentation, but just to remind everyone that NFPA 654, 652, 61, 484, and 664 are good places, places to start. They have a lot of information on the prevention of combustible dust explosions, as well as fires. The primary document that covers suppression and isolation is NFPA 69, Standard on Explosion Prevention Systems. And we are going to be concentrating on the first two items, suppression and isolation. So one last thing here to remind everyone is that if you're interested in the how-tos of explosion protection testing, you can go to astm.org, and these are just a few of the standards for dust testing. Explosion ingredients, as a reminder: you need an enclosure, you need fuel, which in this case is dust. The dust has to be in suspension. You need a dust cloud for propagation to occur, and you need an oxidant, and of course an ignition source. Terminology and definitions. Just a reminder, deflagrations are what we're primarily concerned with: subsonic, self-propagating pressure waves and accelerating flame fronts. Deflagration is the window that we have to work with to control what's going on during the combustion process and preventing enclosures from yielding and exploding by keeping the pressure down to a controlled level. Detonation is the traveling of the combustion zone at supersonic speeds. Once it gets to be that fast, there's nothing we can do really to control it. And then the explosion is the final result where something blows up. KST and Pmax are the primary design parameters of the dust that we use to design systems. We're concerned with the enclosure strength, which per the NFPA definition is 2/3 of the ultimate strength. The ultimate strength being the point at which the weakest structural component fails in the enclosure. P red is sometimes used interchangeably with enclosure strength. So you hear the term P red, reduced pressure, a lot. And then when suppression is involved, we talk about total suppressed pressure, which is the maximum pressure developed in an enclosure during a suppressed deflagration. And then activation pressure for suppression systems and isolation systems, where pressure detection is involved. That's the set point of the pressure detector, and that will typically be in the anywhere from a half a psi gauge pressure to 2 psi is pretty much the range of detection set points for these systems. So an explosion pressure curve, what happens is you're operating under normal pressure, and if we let the there's an ignition, the dust cloud ignites, it starts expanding because it becomes a self-propagating flame front and pressure wave. The pressure rises. If we didn't control that pressure, we would have the red line occur with a rapid increase in pressure until the vessel ruptures, and that's when we have an explosion. And then once, of course, the explosion occurs, the pressure rapidly degrades. What we want to do is use explosion suppression to create the yellow curve, where we have an ignition of a dust cloud, pressure starts to rise, but we suppress that deflagration and therefore limit the pressure to somewhere below the enclosure strength, the yield point of the vessel. And so what we're trying to do is create that yellow curve and prevent the red curve from happening. So our objective is to keep the deflagration from generating pressures greater than the design pressure of the vessel, the enclosure strength, sometimes referred to as the P-red. The concept of suppression is pretty simple. An ignition of a dust cloud creates a combustion event. The heat of combustion develops pressure. And then upon pressure detection in the vessel, we discharge suppressant into the vessel, and that's dispersed very quickly into the entire volume. The flame is quenched, which prevents any further pressure increase. Flame pressure and unburned mixture are contained inside the vessel. And one key thing to understand is that while fire suppression is a thermally activated event, if a fire occurs inside a vessel, explosion suppression is a pressure activated event. So we're reacting against pressure. Here's a little video. Okay. By the way, the most common, by far most common suppressant used is sodium bicarbonate. There are other suppressants out there that aren't much in use anymore. Pretty much everything you will see on the market for a suppression system uses sodium bicarbonate. The system components are a deflagration pressure detector, where we want to sense the deflagration during the early stages, so we have enough time to react against it. A control panel, which monitors the detectors and activates the suppression containers. And then the containers themselves filled with sodium bicarbonate or food grade sodium bicarbonate, which extinguish the deflagration. This is a typical hardware setup. You have a pressure detector. You have explosion protection control modules that the detectors are connected to, and they are the brains of the system. They're constantly monitoring the pressure inside the vessel. There's a and they are the control modules that send a signal when a deflagration is detected to the suppression containers and that discharge the suppressant into the vessel. There's also a power supply module. An annunciator module is basically the window to the system. That's what the technicians connect to on their computers to program the system. Also, the annunciator maintains history of alarms, warnings, the pressure history of the system, and that type of thing. There's a relay module that gives you 8 dry contact outputs if you want to do things like upon a system activation, maybe signal the control room, sound a horn, flashing lights, et cetera, et cetera. Then there's a 24-hour battery backup that's mandated by NFPA. That's a requirement to have 24-hour battery backup with a 20% safety factor built in. And then there's miscellaneous components like surge protectors, electrical surge protectors, and transformers, disconnect switches, so you can disconnect the system, that type of thing. This is a typical suppression container on a vessel. You can also see on the right-hand picture, there's a slide gate valve, a manually operated slide gate valve. That's a NFPA mandated lockout valve. It also has a proximity switch on it, which is connected to the control modules, which electrically lock out the system as well. So it's a combined mechanical and electrical lockout. Again, that's an NFPA requirement. You can see on the left hand that there's like a tube-like thing coming out towards the bottom. That's where the gas cartridge actuator, which is the activator of the suppressant container, that's where that fits in. This is what they look like inside. You have your suppressant. You have 900 psi nitrogen sitting on top of the suppressant. It's held back with a non-fragmenting rupture disc. The removable initiator is the gas cartridge actuator. When that is activated, it creates additional, there's a small plug of material there. Once it's receives an electrical signal, there's an exothermic reaction. Pressure is created from that material, and that additional pressure adds to the nitrogen pressure and opens up the burst disc, the rupture disc, and the suppressant is blown through a zero restriction nozzle into the vessel. This is basically the yellow curve we saw previously. This is what we want to happen in a suppressed event. You have an ignition occur. The cartridge is activated in less than a millisecond. The suppressant is released within 2 milliseconds. And then the maximum pressure is achieved within a few milliseconds, and then starts to degrade well below the enclosure strength of the vessel. And so all this happens within a few milliseconds. Our elements of success, an optimum suppression system must quickly deliver a suppressant amount or sufficient amount of suppressant to stop further development of the deflagration, and that includes early detection, proper location of the containers so that we get full coverage of the vessel within a certain design period of time, and we want to cover the entire hazard volume. Even in very large vessels like big bag houses in coal-fired power plants, very large spray dryers, vessels that have very large volumes, the suppression event from detection to completion, it only takes 200 or 300 milliseconds for the whole thing to be over. So these systems work very quickly, and we need these elements properly applied in order for that to happen. Some pros of suppression versus venting or other types of mitigation. They can be used indoors or outdoors. The process is contained within the vessel and piping. Nothing exits the vessel or the piping. Therefore, there's no safety perimeters that are required. You can stand right next to your dust collector, and if it discharged, there would be a noise, of course, but you wouldn't get hurt. And it does not require a lot of real estate on your vessel, as opposed to, say, an explosion vent, which may take up a very large part of your vessel wall. These are pretty small. Some of the cons of suppression is that they are expensive relative to venting, both in equipment and installation. There's, of course, both mechanical and electrical installation involved here. It does require factory-trained personnel for your system check and startup and configuration. NFPA mandates quarterly inspections by factory-trained personnel. Although NFPA does offer a path to extended inspections, and you can look in NFPA 69 for details about that. But most of our customers do quarterly inspections. Some do twice yearly. There are a few here and there who extend it out to a year, but these are life safety systems, and we don't recommend doing that. Outdoor pressure vessel detectors will require insulation and possibly heat tracing depending on the environment. The reason is because even though the detectors are rated to 0 degrees Fahrenheit, we want detectors to be insulated against anything below 32 degrees, because if there's any condensation that builds up on the detector head, you don't want that to freeze. And that information is in the instruction manuals. So that was a suppression system against propane. You could see a little spark on the right side of that panel. I'm gonna see if I can play it again here. Well, maybe not. Some of the considerations of our metal dust, for example, there's been a lot of research lately in the industry the last several years on metal dusts. There's been some changes to the NFPA standards regarding metal dust explosion protection, with specifically for suppression. Metal dusts require a higher suppressant concentration than organics and hydrocarbons. That's because of the high burning temperature of metals. Metal dusts require, and the higher the temperature, the more thermal energy we have to absorb during the suppression event. Metal dusts require greater quantity of smaller suppression containers to minimize the container discharge time and cover the vessel volume in the shortest possible time. Because with these systems, speed is everything. If we wait more than a few hundred milliseconds, it's too late. So there are limitations with metal dusts, and it depends on the dust, on what the metal is, but there are limitations on the maximum container size we can use for a particular vessel volume, because we want that container to empty within specified minimal times. And then aluminum and highly reactive dusts. Another one might be magnesium, for example, require a 0.5 psi pressure detector set point. Again, it's because of speed of response. We need to detect as fast as possible and as early as possible in order to be successful. So in this case, you want to make sure that you're not going to have normal process pressure fluctuations in the 0.5 psi or higher range. So that's why we want to make you aware of that. Also, for aluminum and other highly reactive metals, our systems are designed for a 1 bar vessel P-red. Aluminum and other highly reactive dusts are limited to a maximum KST of 150 bar meter per second. And now, for the second half, we're going to cover isolation. So why do we need to isolate pipes and ducts? The deflagration pressure and flame will propagate through process interconnections to other plant equipment or personal occupied areas. And that's because the pipes and ducts are dirty, so they contain fuel. That fuel is suspended in usually an airflow. So once the deflagration occurs, then that fuel will also ignite, and now you've got a pressure wave and a flame front propagating through that pipe or duct, and it's accelerating. Deflagrations in connected vessels tend to be higher severity than those occurring in a single unconnected vessel because of pre-compression and flame jet ignition effects. As the flame front accelerates behind the pressure wave, it compresses the combustion gases in front of it, and if that dumps into a connected vessel, that can increase the pressure of the connected vessel prior to fuel in that vessel igniting, and a higher initial pressure in that vessel will produce worse deflagration effects in that secondary vessel. And deflagrations can accelerate to detonation velocity velocity supersonic while traveling through the pipelines. And once that happens, it's just too late. We can't control anything. So the heat of combustion develops pressure in the vessel, which then, of course, can ignite the fuel in the ductor pipe. So upon pressure activation or pressure detection and sometimes optical detection, the isolation device is activated, and we'll look at different isolation devices. But that will then prevent flame and sometimes pressure, not always, but sometimes pressure from propagating through the duct or the pipe. And once that isolation device is activated, then the flame, pressure, and unburned mixture are contained inside the duct and the pipe, as it also is contained in the vessel if the vessel has been fitted with suppression. Sometimes you need optical detectors on isolation systems, and the reason is because under unique conditions that involve very large volumes of vessels and or very low rates of pressure rise inside the vessel, it's possible for the fuel in the pipe to ignite before the pressure is detected at the wall of the vessel by the pressure detector. And in that case, we put a optical detector on the pipe just outside the vessel to look for that flash of flame entering the pipe. So you occasionally may see an optical detector on a pipe. That's not common, but sometimes it's required as a backup to the pressure detector. And our objectives are preventing that deflagration from traveling to another part of the process, another part of the plant, and transitioning to detonation. If you look at some of the major explosions over the years, you would find that many times the greater damage was due to secondary explosions, not the initial deflagration, because it traveled through pipes and ducts to other areas of the facility, creating noise, vibration, dust going up into the air, becoming suspended, then igniting, and it's important to isolate that from happening. So a common type of isolation device is a flap valve. It's basically it's very similar to a check valve. It's a unidirectional valve, often used on the inlet ducts for dust collectors. And it's a very simple device. You have a flap, your normal airflow, the flap opens, and during a deflagration event, that flap is slammed shut and it's latched so that it stays shut, and that stops the pressure wave, and it stops the flame front that's traveling behind the pressure wave. Some pros of flap valves and why they're popular. It's a low cost device for dust collector inlet duct isolation. It's a positive barrier against flame and pressure. It's activated by the deflagration pressure wave, so no controls are required to activate it. As such, you don't need a detection system, and therefore inspections and maintenance can be done by the owner, and it can be reset by the owner. NFPA does not require factory-trained personnel to maintain these devices. Some cons is that some of the larger sizes, because it's a metal valve, it's a steel valve. Some of the larger sizes, depending on how robust the ductwork is, may require some additional supports. They are subject to dust accumulation around the flap seat, and if dust accumulates around the flap seat, they won't close properly. So therefore, NFPA 69 requires dust accumulation sensors, or in lieu of sensors, accelerated inspection periods if approved by the authority having jurisdiction. They're not always approved for metal dusts, so you have to check with the manufacturer if your process is a metal dust process. They are not allowed for installation in anything other than horizontal ducts or pipe sections. You can't put them on vertical pipes. And being a check valve, it adds pressure loss to the system. So you have to account for that. Another type of isolation valve that's recognized in NFPA 69 is a float valve. And float valves are for clean air ducts and pipes. There's limitations on how much dust can be in the flow stream. And it's a minimal amount. And the way these work is that this float is held inside this valve chamber by springs, and during normal flow, the flow flows around that float and continues downstream. And then if a deflagration occurs, that deflagration pressure wave slams that float against the opposing seat and isolates against that pressure wave. So because these are for clean flow streams, it's a pressure isolation device, a deflagration pressure isolation device. So you can use these and use them as passive isolation for dust collector clean air return ducts, because they're not only unidirectional, they can be bidirectional. Another application would be dryer, like a spray dryer inlet air pipe, and other clean air, gas, and vapor applications. You can use these for, flammable vapor isolation in pipes. You can use this for air inlets to grinding mills, things of that nature. It's a positive barrier against flame and pressure. It's activated by the deflagration pressure wave, so no controls are required. Again, same as the flap valve, they're resettable by the owner. They're approved for gases and vapors, unlike a flap valve, which is for dust only. They are approved for metal dusts. You can put them in horizontal or vertical installations, although we need to know that because there's a slight modification that needs to be done to the valve for it to be in a vertical pipe. And bidirectional models are available. They're very expensive, roughly, and this will vary by size, but it's between $1,000 and $2,000 per inch of valve size, and they start at 4-inch and go up to 24-inch. They're limited to 25 meters per second flow velocity, dry airflow less than 50 grams per cubic meter dust air concentration, and less than 0.5 millimeter particle size. So those are the restrictions on any dust that may be in that flow stream. They're very heavy and require substantial supports. Maintenance and repair is done by factory certified personnel. Now your own personnel can be factory trained, but they need to be factory trained. And in certain types of repair, they need to go back to Fike or whatever supplier you're getting them from. And they do add pressure loss to the system because there's that float in the middle of the flow stream. Now, by far, the most common type of duct and pipe isolation we sell is suppression. The terminology is chemical isolation, but it's the same as explosion suppression of vessels, except we're applying it to ducts and pipes. And that's what a typical suppression container for ducts and pipes would look for. Duct and pipe diameter is less than 20 to 24 inch, depending on the application. Larger duct sizes would take either larger quantities of this container or larger containers. It's the lowest cost option when used with vessel suppression. If your vessel has explosion suppression system on it, then this thing just plugs into the system. So it's usually, and the larger the duct, the greater the cost savings to just add chemical isolation to your existing pressure detection system, your existing suppression system. It can be used indoors or outdoors. And by the way, the low temperature limit for suppression containers is -30 degrees Fahrenheit. The process is contained within the piping. No safety perimeters are required. It's approved for metal dusts and gases and vapors, and there's zero pressure drop in the duct or the pipe because the nozzle, the discharge nozzle of the container is flush to the wall of the duct or the pipe. Unlimited duct and pipe sizes. We've applied chemical isolation. I think the largest duct we ever did was about 7 feet in diameter. It's simply a matter of how much suppressant you discharge into that duct. Suitable for inlet and clean air return ducts, horizontal or vertical installations. We can supply hygienic nozzles for hygienic applications, and it's not subject to dust accumulation. It does require factory trained personnel for system check and startup. Just like a suppression system, it requires NFPA mandated quarterly inspections by factory trained personnel. Requires insulation and possibly heat tracing of the pressure detectors for the isolation system. Metal dusts may require additional suppressant concentrations depending on what the metal is. Steel dust usually doesn't, but it's on an application by application basis. The cons of explosion isolation are it's not a positive barrier against the pressure wave. So what happens is we're discharging suppressant into the pipe, and that suppressant is removing the heat of combustion from the flame front traveling through the pipe, and that quenches that flame. However, there's still a pressure wave traveling down the pipe. Now, because there's no flame front feeding that pressure as it travels down the pipe, the pressure wave starts to degrade. And usually it degrades sufficiently that that pressure wave really is not a factor anymore. But if you are concerned about positively stopping that pressure wave, then you want to use something else other than chemical isolation. You want to use a valve. It may require some additional cleanup of the ducts because they're full of suppressant. And then if you're putting it on a clean air return duct on a dust collector, you want a filter or other barrier to prevent the suppressant from blowing into the room. So that's what goes into the pipe. Another type of isolating device is a high-speed gate valve, bidirectional gate valves. Hygienic models are available, and these valves close in 5 milliseconds per inch of valve diameter. So a 10-inch valve, for example, closes in 50 milliseconds very quickly. And that's what they look like. So at the top is a junction box, electrical junction box, and it's attached to a gas cartridge actuator, same as identical to the ones that are on the suppression containers. And that creates the pressure which drives a piston down and drives the gate down. And again, this all happens very quickly. Some of the pros are positive barrier against flame and pressure, zero pressure drop. You can use them on metal applications and gases and vapors, as well as horizontal or vertical installations. They're not subject to dust accumulation, and hygienic valves are available. Cons are this is the most expensive isolation solution. They're limited to 24-inch. Even though they close very quickly, they don't close anywhere near as quick as a chemical isolator or the flap or float valve. And so they need they need to be placed farther away from the vessel to give it time to close before that flame front and pressure wave reaches the valve. Substantial weight and dynamic loads. You can imagine, you know, a valve traveling at that kind of speed slams into a seat, and that requires a significant structure to hold that valve and prevent any of that impact from translating to the pipe or the duct. And it requires factory trained personnel for system check and startup because it's a pressure detection system for this valve, same as suppression devices. Requires quarterly inspections, and because there's pressure detectors involved, you need to insulate or heat trace if they get cold. This is a photo of one. I believe that was a 6-inch on a clean air exhaust from a indoor dust collector. And there's a filter on the end of it for normal operation, when the valve is open during normal operating conditions. Another type of valve that you see out there are pinch valves. Now, this has a rubber tube, and we use the pressure detection system, which activates a high-speed solenoid valve, which applies plant air to the valve casing, which pinches the tube to close against deflagration, flame, and pressure. Now, these types of valves, we find them used in possibly some more abrasive situations, like sugar dust, for example. We've provided these to sugar processing facilities. That seems to be a common application for these devices. It provides a positive barrier against flame and pressure. It's expensive, but it's less expensive than the gate valves. There's almost zero pressure drop because basically that tube is a full diameter tube, so the only pressure loss is due to the length of the valve, which is practically nothing. There's no dead spaces, and there's no reaction forces you need to worry about because the tube is being pinched from both sides, and so the reaction forces negate each other. So there's no substantial supports that you have to build for this thing other than to carry the weight. Horizontal or vertical, no dust accumulation. It's resettable by plant personnel, and the tubes can be replaced by plant personnel. So this is a reusable valve, and you should be able to get 3 or 4 maybe deflagrations before having to replace that tube. And if you're getting 3 or 4 deflagrations, you probably have other issues you need to worry about. Because that should be a rare event. They are expensive, like I said, but they're a little bit less expensive than the gate valves. They are limited to 12-inch and a KST of 200, and that's the 12-inch size is due to the speed of closure. They are the slowest valve and slowest isolation device. It does require 85 psi plant air. Because they are the slowest devices, they require a substantial length of duct or pipe for installation. The weight can be heavy, but like I said, there's no impact, no reaction forces, so the weight is the only thing that you're going to have to support. And it does require, because it's a pressure detection system, factory personnel for initial system check. And it also requires mandated quarterly inspections because it's a pressure detection system. And again, the detectors, if they're outdoors or subject to cold, they need to be insulated and possibly heat traced. So that's really it. We're 5 minutes short of an hour. So if anybody has any questions, we can discuss anything you want, or feel free to email us or call us later if you want to discuss something in more detail. And I'll hand it over to Alex.
Thanks, Tony. Did have a few questions come up. One was regarding dust testing, and I know that we've covered that in earlier classes, the part 1 and part 2. But just so everybody knows who watches this, dust tests are the best way to find the properties that are required that Tony was referencing, to see which type of explosion protection solution is going to work best for your application and your material. So if you need help with that, please make sure to reach out to the Dale Prentice Company, myself or Tony, and we can get just heading to our website on prentisco.com or VRC Protx, and we'll make sure to get you set up with that. The next one was on metal dust. Tony,
Alex, let me interject something.
Yep.
The primary dust test is the explosibility test, which is ASTM E1226. That generates an accurate dust KST value and an accurate dust P max value. That's what we use to select equipment, the proper equipment for the application, and to design these systems. And also, it's required if you're applying explosion venting, which we discussed last week. The KST and P max values of the dust are parameters that we have to enter into the equation, the vent area equations. We can't calculate vent areas without those values. And so it's important for your protection and to make sure that whatever you're applying to your equipment, that it be accurate. So that test gives you accurate numbers. Now, there are some variations on that, and if you say, for example, I don't have a dust test for this because the process doesn't exist yet, for example, but based on research, it's going to be a ST1 dust. So design the system for a KST of 200 and a Pmax of 10. That is okay with us if that's what you want us to do. But the dust test is what we strongly encourage and NFPA encourages. Another test that's becoming more important in not only selecting equipment, but also making decisions about what is how we apply the equipment to your system is the minimum ignition energy. So while it's not required generally to offer a quotation to you, knowing the minimum ignition energy of your dust can help us make sure that you're getting the best solution, not just a solution. So we encourage you to get the explosibility test and the minimum ignition energy test. Now there's a long list of tests that you can do, but those two are the primary ones.
Perfect. Thanks, Tony. Like I said, reach out to VRC Protx, and we can get you set up with dust testing as well. There was another question regarding metal dusts, Tony, and passive isolation systems. So I know that gets a little custom and needs to be reviewed by the Fike team, as well as for most you're going to have a dust test completed for that. Do you want to add anything else for that? I believe you covered it a little bit, but
well, NFPA 484 is the standard for metals, and they say that if you test metal dust in the 20-liter explosibility test, which is what most people use. They have their dusts tested in the 20-liter test because it's less expensive and it only requires a 2-pound sample of dust to perform. That there are correction factors applied to the KST results of that test, depending on what the metal is. So, for example, we do a lot of steel shot blast applications, and for steel dust, if you had your dust test done in a 20-liter vessel, per NFPA, we have to increase that KST by 40% in order to calculate an explosion vent or design our suppression systems. So they encourage you to, any metal dust, get it tested in a 1 cubic meter test. Now, because the 1 cubic meter, for a variety of reasons that we would be happy to discuss later, but the 1 cubic meter test is more accurate than the 20-liter test, which is only 0.02 cubic meters. The reason why everybody just doesn't get their dusts tested in 1 cubic meter vessels is because A, it's more expensive, and B, instead of sending the lab 2 pounds of dust, you have to send the lab 66 pounds of dust. That's 30 kilograms. So, that's a 55-gallon drum of dust. So we would encourage you, any dust test you do for metal dust, do in the 1 cubic meter test, because that would be more accurate. They've found, research has shown that the smaller vessel test does give inaccurate data a lot of the time, and so that's why they do that. Alex?
Thanks, Tony. I appreciate that. I believe that's all the questions that we've had. If you watch this later and you have any questions, concerns, or just like more information, please reach out to VRC Protx or the Dale Prentice Company. Our numbers and contact information are listed on our websites, vrcprotx.com and prenticeco.com. Thank you for joining. And Tony, I appreciate your time. Have a great week.
Goodbye.